Okay, I guess we can start. Welcome everybody, new German club. Today I'm hosting the German club since both the representatives are missing. And we start with Michele Fiori with, is there a giant Kelvin-Helmholtz instability in the sloshing cold front of the Perseus cluster? So yours.
Hi everyone. So first of all I want to tell you what is a Kelvin-Helmholtz instability. A Kelvin-Helmholtz instability is a type of fluid dynamics instability that occur when two fluids are in relative motion between each other. So in this work they consider the two fluids are the hotter and colder intercluster medium found in the core of relaxed galaxy cluster. As we can see from here, from the Perseus cluster, we see in this case, so in the past has been has occurred minor merger element that induce gas sloshing and produce these features in the cold gas. We see that there is the possibility of formation of Kelvin-Helmholtz instability, and probably is the formation of this bay, this concave structure, is could be explained by this type of instability. We see here we have a Chandra image in X-rays, and on the other panel we see also the radio contours overimposed. We see these features, these bay-like features, also in other clusters like the Centaurus cluster and in this Abel 1795 that is not clearly seen here, but from the radio contours is much easier to see. So these unusual concave bay-like features are difficult to explain. There are maybe some AGN feedback process, or it's just gas sloshing of this cold gas. For when we have a cold gas that is sloshing, we expect a temperature that increases from the more dense side, so in the direction of the galaxy cluster center, and to the less dense side, so outside the bay. So, but we expect convex curvature instead of concave curvature. A possible explanation could be AGN inflated bubbles, but these bubbles should be filled with a radio-emitting electron, relativistic electron. So we expect a big flux in radio that we are not really seeing. And so one explanation is this Kelvin-Helmholtz instability that can create rolls with this type of curvature. So they start studying the bay properties. Here we see the two of the clusters they have studied, the Perseus and the Abel. We see the behavior of the temperature, of the metallicity, and the surface brightness. Of course, the surface brightness is decreasing between the edges of this bay, and we see from the black line. The other lines I will explain after what are. So the temperature are increasing from the, as I said before, from the dense side to the less dense side, and the metallicity is decreasing. This decreasing in metallicity is in disfavor on the model of the AGN bubbles, because if there is an AGN bubbles created by AGN, we expect an increase in metallicity, not a decreasing. And we see the same behavior in the Hubble one. So, other properties we can see is that the direction of the base is just, so we found the base only on one side of this cluster. And the direction are at almost 130 degrees from the direction of the main cold front. Also, we see that it is similar between these two clusters, but we have to stress out that the two clusters have a different dimension, so it could be possible it's just a coincidence that it's like this. So they start studying the possibility of the cavity scenario, so the Aegean bubble properties scenario. So they use a cavity toy model, and they compare with the observation, with Chandra observation. So they see that the surface brightness is expected far more severe than what is seen. Also, the temperature increasing is the green line is much lower than what we are seeing. Also, it's not possible to reproduce a cavity toy model that matches both jumps in temperature and surface brightness. So, in order to study the possibility of formation of this base due to Kelvin-Helmholtz instability, they made some simulation of gas that is sloshing after a merger with as we can see here. So after 2.3 gigayear, we see a concave structure that is forming and is stable until 2.5 gigayears. This is really similar to what is seen in the Perseus cluster. They made many simulations changing the initial ratio between the thermal pressure and the magnetic pressure, that is the parameter beta. In this simulation, the parameter is 200, and they say that if we increase the magnetic energy, so we increase this, decrease this value, there is a suppression of the of producing this type of structure, because the magnetic field inhibits the instabilities, while increasing we see much more concave structure that we are not seeing in the case of the Perseus cluster. We see how there is striking similarity between location and size at the bay, and also we see that the temperature profile are in a good agreement as the surface brightness behavior. They say that with this model it's possible to put some constraints on the thermal pressure to the magnetic pressure ratio. So, conclusion. So they investigate the origin of this bay, and which they found in 3 nearby clusters. The temperature jumps and the surface brightness jumps are consistent with the cold fronts, so but in this case concave instead of convex. They compared the simulation with the data, the real data, and they found that the properties of the base are consistent with large Kelvin-Helmholtz rolls, and that there is a very good agreement with the data for Perseus cluster, with the same dimension and also the same direction of this bay, with parameter beta of 200. This could be a very important tool to investigate the magnetic field inside the intercluster medium, whilst it is possible to port only an order of magnitude of on this magnetic field, and not precise constraint due to the fact that there is many parameters that change the structure of this Kelvin-Helmholtz roles. Thanks.
Thank you, Michele. And questions?
I have to confess my ignorance, but I find the language a little difficult to understand. So when you talk about concave, and also when you talk about the Kelvin-Helmholtz roles, what does concave actually mean, and what are the roles?
From here,
Yeah.
we have this instead of convex radius here we see
with respect to the center.
yes,
Okay,
respect to
sorry.
the center of the rows is something like that is forming here.
Okay, so it's not like round.
No, it's,
And what's a role? I know
I-
about the Kelvin-Helmholtz instability, but not about the role.
I think they just because they didn't mention anything, they talk about this like Kelvin-Helmholtz roles, and I think this structure that is forming a round structure that is forming.
It's a round structure. By the way, it's magnetic, not magnetic, like in
okay.
So the origin of this, you said, is a merger.
Yes,
Is the merger between two cluster of galaxies, or is just the infold of one galaxy?
an infold of one galaxy. Yes, just a minor merger.
Because it looks
They-
very similar to the tidal, that was that, I don't remember the name.
Tidal tails.
No. Okay, I will tell you later, but there's the same, every time that you have a dwarf galaxy passing through the intergalactic medium, it is possible that these galaxies lose its gas contact, transformation stops, and you have this feature in the contrast.
Other questions? Okay. Thank you very much, Michele. And now I have to introduce myself, since we are missing our presenters. So, today I'm going to talk to you about the Triton's evolution with a primordial Neptunian satellite system. And to start, I wanted to show you these nice infographics produced by the Planetary Society, in which you can see all the major moons of the solar system. And it's noteworthy that all the gas giants have pretty complex and numerous satellite systems, like Jupiter with its 4 Galilean moons. These are all to scale. Saturn with 7 major moons. Uranus with 5. The Earth, which is quite the outlier in our system. And Neptune, which just has Triton, and the next largest moon is Proteus, which is more like a pile of rubble. So, why is that? Why do we see this regularity in the gas giants? And particularly an important parameter is the moon system to planet mass ratio, which is more or less consistent across all the system, and is 10 to the minus 4. But while in Jupiter, Saturn, and Uranus, this 10 to the minus 4 of the planet's mass is distributed across several satellites, in Neptune we just have Triton. And another important thing is that Triton is highly inclined, 157 degrees. It's more than 90 degrees, so it's actually retrograde, which is against what we observe in all the rest of the solar system, in which the satellites actually lay on the equatorial plane, or more correctly, on the Laplace plane of the system. So why is that? The first proposed explanation that comes to your mind is that Triton is not an original satellite of Neptune. It happened somehow around Neptune. And the most probable scenario is that Triton was captured from a wide Kuiper belt object binary, which passed by the Neptune system. One body was captured and the other was ejected. So, clearly, Triton's capture has destroyed, if there were any, the original moon system of Neptune. And with the simulation proposed by the authors of this paper, it is possible to place an upper boundary to the system's original mass. So to confirm if this rule of thumb is actually valid also for the primordial satellite system of Neptune. Of course, the initial high eccentricity of Tritons, because of its capture, has caused all sorts of dynamic interaction. It's a very complicated scenario. But the question is, how did we come to today's situation? So, methods. The authors decided to perform an n-body integrations using this code by Duncan and al. They set up an hypothetical prograde satellite system and evolved all this for 10 to the 7 years, including the effects of Neptune's oblateness and, in a separate set of simulation, also the presence of the tidal interaction with the Sun, which at the distance of Neptune are much less important. So this grid of 600 simulations explores 3 initial Triton inclinations. So we have today's inclinations of extremely high inclination. This is completely retrograde, 180 degrees, and 105 degrees, which is more or less perpendicular to the planet's equator. And they tried the different sets of semi-major axis and periapsis of the captured Triton, and 3 sets of primordial satellites masses, so 0.3, 1, and 3 masses of the Uranian satellites, which are our case of reference, because as you know, Uranus and Neptune has quite similar masses. They differ by 15%, something like that. So if we assume that this 1.04 times 10 to the minus 4 mass of Uranus, this is applied also to Neptune. The primordial system consists of 4 satellites, which are similar to Ariel, Umbriel, Titania, and Oberon, which are Uranus major satellites. And they are scaled to Neptune's mass, while their semi-major axes are either kept scaled to Neptune's scale radius or just taken as they are in the Uranian system. And this is a bit more detailed. This is the grid of simulations. Here you can see the initial conditions, the initial semi-major axis, the initial periapsis, the initial eccentricity. And these are the results for the 3 different primordial moon system masses, divided by the output of the simulation. So a Triton survival, the fall of Triton onto Neptune, and the ejection of Neptune. And as you can see, you can already see some patterns, like a very low mass primordial moon system actually grants many times the survival of Triton, while heavier systems are more likely to either destroy or eject Triton's moon. So, further in detail. First panel I want to show you is the relative velocity of the impacts, because of course when Tritons enter the system, it excites the system, and the orbits of the moon can cross each other and start to impact. So here we have the distribution of the relative impacts between the original Neptune moons, and these are the velocities of the impacts on Triton. As you can see, the distribution is much more higher, has a mean value much higher for Triton, because Triton is retrograde, so it will intercept head-on the original moons of Neptune, while the relative velocities between the Neptunian systems are much lower. There is an increase of the mean of this distribution with the decrease of the mass, because less massive moons are more easily excited by the presence of the interloping moon. So, high velocity impacts, of course, can cause the Triton's collapse onto Neptune by removing the orbital momentum of the moon, or the complete disruption of Triton. If it survives, it is usually the last standing object, which is what we actually observe today. And of course, Triton survival rate, as I was saying, decreases with the increase of the primordial system mass. And the impacts on Triton, you can see that the number of impacts decrease with the mass of the system because Triton is lost earlier because of this stronger interaction. Another point that the authors analyzed are the disruptions with theoretical description in the paper. These are the impact phase space for the three masses of the system, the three putative systems. And this is the disruption phase space according to relative inclination. So more shaded areas have a higher probability of disruption. Here are 45 degrees, and here is 0 degrees of relative inclination between the two impacting moons. In pink, you can see the impacts on Triton, and in green, the impacts between the primordial moons. While black dots represent disruption events. When a disruption events occur, the material is distributed in a accretion disk, which is usually reaccreted in the Laplace plane of the planet after 10 to the 2 years. And this is questioning the results of Cook and Gladman, 2005, which said that Triton's circularization, which is the main problem, because we see a highly circular orbit of Triton around Neptune, happened because of interaction with the debris disk. The debris disk is accreted back into a new moon, in 10 to the 2 years, because the tidal synchronization time is much higher, 3 orders of magnitude higher, 10 to the 5 years. Of course, impacts on Triton are more disruptive than between satellites because they are higher velocity. Final, orbital synchronization. One of the conditions the authors imposed is that the final semi-major axis of Triton must be smaller than the semi-major axis of today's Nereid. Nereid is the innermost of the irregular satellites of Neptune, and the authors assume in this paper that Nereid was not created after Triton's arrival, but it is actually a primordial irregular satellite of Neptune which actually survived Triton's arrival. So one of the main conditions is that the circularization of Tritons must ensure Nereid's survival. And as you can see, a low mass system, these are the final positions of Triton according to the semi-major axis. In red, you see the semi-major axis of Nereid. In green, you see today's inclination. You can see that in the low mass system, the inclination is not a low inclination initial scenario. The inclination is preserved, so it doesn't explain what we see today, because we see Triton here today. And extremely high inclination, again, does not allow for today's Triton. While very high mass in the primordial moons, again, does not ensure the survival of Triton in the region we expect to find it, because we see it there today. Another point is that circled dots are Triton analogs that did not suffer any impacts. And as you can see, they are all very far on the left of the graph. And that means that the scattering alone does not reduce Triton's capture orbit enough. Impacts are necessary. So what we see, today's Triton may not even be the original Triton, because it has been reshaped and resurfaced by the impacts with the original Neptunian moons. This is an area, the shaded area is where quasi cycles happen, and these excite the eccentricity of Triton and actually forbid it to actually interact with the primordial moons. So the tidal synchronization times are much longer if the moon stays here for a long period. But not enough to avoid the stabilization before tidal synchronization starts. So this is a good result. So, in discussion, as we can add the percentages. these are quite important because here these are the percentages of Triton analogs that both survive stabilization and do not experience disruptive events. So you can see it's much higher, 81% for low mass systems than for high mass systems. Of course, because the system is more massive, the impacts are more disruptive. But because of this effect, these are the percentage of Triton analogs that survive circularization, does not experience disruptive impacts, and allow for the survival of Nereid. And as you can see, this percentage goes down from 81 to 36%, while the other goes down from 36 to just 21%. So it's a much stronger effect here than here. So in discussion, the collisions are not disruptive, and the formation of a debris disk is unlikely. If this disk is formed, it is quickly reaccreted, and so it does not contribute to Triton's orbital decay. A primordial satellite system of 0.3 to 1 Uranian satellite masses has a substantial likelihood for the survival of Triton while maintaining its high inclination, which is important, but only a system with higher mass than 0.3 allows for the Triton's orbital decay in times that allow for Nereids and other irregular satellites' survival. The solar perturbations strongly affect these quasi-perpendicular orbits, also for with quasi-cycles, and 88% of the moons are cannibalized by Neptune. So, in conclusion, the authors respond to a long-standing question. We knew that Triton was captured somehow. The point is that they conclude that a primordial satellite system of a mass ratio comparable to that of Uranus can allow for what we see today and preserve the existing irregular Nereid-like satellites. So this is a further confirmation that that little number, 10 to the minus 4 of the planet's mass, is more significant than what we thought. So maybe other gas giants, I will think of exoplanets, should have this ratio also for their moon systems. And yeah, this is another thing that I quickly said. And so thank you for your attention. No questions.
What do we know about Mercury, Mars, and Venus? Are we sure they don't have an
Mercury and Venus are too close to the Sun to have satellites which are stable for timescale longer than the age of the solar system.
Why is that?
Because their hill radius, the orbital, the space around the planet, which has stable orbits, is much smaller than in the outer solar system because they're closer to the Sun. So the tidal effects of the Sun quickly disrupts any satellite. An example is the Messenger mission around Mercury. It was put in orbit around the planet, and in 5 years the orbit was quickly disrupted and tidal deformed by the Sun itself. When the onboard fuel ran out, the spacecraft simply crashed onto Mercury. And this happens also for Venus. They could have smaller satellite, but for much smaller timescale than the age of the solar system. So anything they had of primordial is lost.
How about Mars?
Mars this is a good question because Mars is very close to the elephant in the room, which is Jupiter. And Jupiter has greatly influenced Mars formation and evolution. So if Mars had an original satellite, it could have lost it to the asteroid belt, fundamentally, because there are a lot of dynamical interaction going on. Mars has not a large mass, it's just 10% of that of the Earth, so its hill radius is much smaller.
You mean a large satellite? Much larger than Phobos and Deimos?
Yeah, because Phobos and Deimos, even though they are in the equatorial plane of Mars, So you might think of common history of formation between the two objects, between Mars and its present-day moons. They are most likely captured asteroids, which were circularized by tidal interactions.
What Mars is mass?
Mars has a mass that is 10% that of the Earth.
10% only?
Yeah, only 10%, because it's half the radius and half to the cube is an eighth. So it's more, and it's less dense. So it's just 10%, and that means that it cannot hold onto its moons very long. In fact, Phobos is actually falling onto Mars because of tidal interactions, and Deimos is actually escaping. So the two orbital radii, one is decreasing, the other is increasing. Phobos is so low in Martian space that you can actually see it rise in the west and set in the east, because it goes faster than the rotation of the planet.
Something semantic. For you, irregular is opposite to primordial.
Okay, this is a planetary science term. For irregular satellites, they mean non-spherical satellites which are in highly inclined orbits around their planets out of the Laplace plane. So they may even be retrograde. For example, I was showing, these are the major moons of the gas giants. There are other moons which are considered regular moons, principal moons, which are usually inner than the innermost. So the Jupiter has 4 moons inner than Io, and Saturn has billions of moons, which are more inner than Mimas, which are the rings and the shepherd moons. While also Uranus has a lot of shepherd moons for its very, very thin rings. While Neptune has some inner moons, but they are just like Proteus, piles of rubble, which are probably formed from the debris of the various collisions that Triton caused. Outer of the outermost regular moon, there are tens and tens of these irregular moons. For example, Jupiter has 4 inner moons, 4 major moons, and then 62 other things, which are categorized in groups according to their orbital parameters, if they are counter-rotating or co-rotating with the planet, if they have a particular set of inclinations, and they are mostly, all of them, capture comets or asteroids. With that they mean irregular. If Nereid, which is a third of Proteus as a dimension, is actually primordial irregular satellite, so it's been there, it's been captured at the dawn of the solar system and Triton has not disturbed it, or it is something that was captured later, we do not know, and we cannot know because it's dynamics. Other questions? Okay. Thank you very much. And see you next Monday. Giuliano will tell you what will happen, I think. I know nothing now. I'm no longer that person.